All right, let's get this party started. It's a beautiful day out there. I want to thank you all for separating yourself from the food, which is fantastic. But I just want to welcome all of you. This is the Dean's Lecture Series, and this is really to get the broad audience from across campus, for the faculty, for the students, for the staff, and we bring in a thought leader to speak on issues that we all care about. The Dean's Lecture Series was created to form some kind of a discourse and to identify opportunities and to learn, frankly, on things that don't neatly fit into a departmental seminar because they're just cross-cutting. And you had the first Dean's Lecture Series was on environmental justice. We had one on data by Guha Ramanathan and data commons. We had one, the last one, I believe, was by the president of Indonesia. So, Will Marshall, no pressure on you. But today, it's a great opportunity to welcome Will. But just to give you a little bit of idea what we're talking about, we have some amazing research going on campus. But that could be enhanced. Even just last week, we had a paper in Nature from Adam Brandt's lab on measuring methane emissions in the United States to find out where the emissions are coming from. Amazing result. It came out in Nature last week. If you haven't seen it, take a look. And we are living in the age of AI where data becomes very, very important. But to really lean into this, you need partnerships. You need to have a source of satellite imagery of all different kinds, different spectrum, different resolutions, spatial resolution, spectral resolution, and then use the AI to do things. And it is really a tremendous opportunity to learn from today's speaker, and that's Will Marshall. Will is the chairman, co-founder, and CEO of Planet, and he founded this in 2010. And Planet designs, builds, and operates a fleet of imaging satellites that provides global and daily satellite imagery and geospatial data. They currently operate more than 200 satellites in orbit, collecting 350 square kilometers of imagery per day. Prior to co-founding Planet, Will was a scientist at NASA, where his work included lunar orbiters and nanosatellites. The World Economic Forum recognized him as a young global leader, and he also serves on the board of Open Lunar Foundation. He holds a PhD in physics from the University of Oxford. Please join me in welcoming Will.
Well, thanks a lot for that kind introduction. Lovely to be here with so many familiar faces and new. Looking forward to this discussion and really want to make it a discussion, not one way, obviously, and I think we'll get the most out of that. I think the most important thing I want to impress upon everyone here, if there's one message, is just I think the profound underutilization of the new data sets that we have from satellites. They're underutilized in how they can have a real impact on the world, not just a research impact on the world, but a real impact in enabling us to transition to a sustainable economy and a sustainable planet. And so that's what I hope to talk a tiny bit about here today. What did I do? Did I break it already? Nope. All right. I'll give a few slides. There's a number of questions that I'm happy to answer. So yeah, we started Planet about 12 years ago with setting ourselves the goal of imaging the whole Earth every day. So regular scanning of the Earth had been done for about 40 years prior to that with Landsat, but at a 30-meter resolution and roughly every 16-day revisit time. And a lot of things, oh wow, that's sophisticated errors to go there. So a lot of the mission was about getting on the human timescale of changes. You can't manage what you don't measure, and human changes to our spaceship Earth, have been happening on days and weeks, and you just couldn't catch that in the Landsat data. and or at the Landsat resolution. So the goal was to supplement that with higher resolution, higher frequency imagery. And so we set ourselves the goal of imaging the whole world every day and making that visible, accessible, and actionable. And actionable being the most key thing, because we've got to act to change our present trajectory, as you guys are all familiar, I'm sure. We went public as a public benefit corporation, which is a new legal form which bridges between a sort of pure for-profit motive and a non-profit or sort of motive. And in particular, this I just touch on this for a second, because I think if you're thinking of starting a company, it's really interesting to think about this form. You literally get to write the mission statement into the DNA of the company. It's not like a B Corp where you can say, oh, in principle, we might care about other shareholders and stakeholders to our stuff. This writes it into the DNA of the company, which means it's the fiduciary duty of the directors of the company to care about your mission, which in our case is essentially using space to help life on Earth. And so it was interesting when we went public, our outside counsels came around and these lawyers told our board members that if they don't save the planet, they're going to get sued, you know? It was a pretty cool situation. Anyway, I digress. So this is how our fleet of satellites works. So we have, as was mentioned, about 200 satellites. They're in a sun-synchronous orbit, polar orbit, about 400 kilometers to 500 kilometers at altitude. Each one takes a strip of images as it goes over the Earth's landmass. The Earth does the legwork. The plane of satellites stays fixed with respect to the sun. That's the sun-synchronous piece of it, so it's the same time of day. The Earth rotates underneath every 24 hours, so you line scan the Earth every 24 hours, and that's at 3-meter resolution in 8 spectral bands. And then we have a second fleet of satellites, that about 20 of those are 50-centimeter resolution, and they're tasking systems. So they're in 4 different orbital planes that you're starting seeing the mess of different orbits there. There's 2 inclined planes and 2 polar planes that enable us to revisit any place on Earth up to about 10 times per day. So if you say, I want a picture of Tahiti or wherever you want to go, we can do that up to 10 times a day, but that's a task system. So I'd rather think of this like the human eye, and AI is an important thing that will add to these 2 foundations, but essentially the human eye has a very wide peripheral vision at medium resolution. Actually, it's black and white after about here, and then it's only high resolution in a tiny piece of the field of view. But we're very good at change detection in our medium resolution scan, and when you see change in your peripheral, of course, you move your head or your eyes to take a high resolution snapshot. So the goal of these combined systems is the scan finds changes, the high res zooms in, and it's the AI that's doing the legwork that the human cortex, the visual cortex, is doing to detect that change detection that enables you to zoom in. So this is our fleet today. The top 2 are where we have the satellites up in orbit, and the bottom 2, we're launching a new 2 set of satellites. The Pelican one on the right is a higher resolution version of the SkySat, which we had inherited from Google. Those ones were initially at 70 centimeter resolution. We increased it to 50 centimeter resolution by lowering the altitude. We're going to 30 centimeter resolution, but even more importantly, with satellite-to-satellite communications on those satellites, we can get the data back within 30 minutes so that we can respond to disasters and things like that faster. At the present, it takes a few hours, so about a 10-fold increase in the timeliness of getting the data back, which for certain applications matters a lot, less so for research. But and then Tanager is our hyperspectral fleet of satellites, which I'm really excited about because they have a big role in biodiversity. Although the main program that this is for is a program called Carbon Mapper, which is about mapping point source emitters, particularly methane emitters around the Earth. This one has 30-meter resolution, so it's broader pixel size, but it can, down to the facility level, tell methane facilities that produce methane with sources as small as 50 or 100 kilograms of methane per hour. So California, there was an airborne study of California of all the different emitters, their size and frequency, And this was aimed to get at 90% of the emitters, not just for California, but for the globe. So basically taking an airborne survey and doing it for the world. So the first of the Pelicans just got launched a few months ago. So it's testing that satellite design in this process we call Agile Aerospace, which led to all the others. And Tanager's first satellite is literally built in our lab, going through testing, and then will be launched later this year. First one of them, and we aim to have fleets of both of those, but we always test and improve. So a little bit of by the numbers, just give you a sense of the scale. We image, I think, so the Earth's landmass is 150 million square kilometers, so we only image for shore every day, the whole landmass. We don't image all the large oceans. We do image some of the ocean areas, like the Caribbean, the Mediterranean, and South China Sea, and a few other places, but we don't do the whole high seas. But we do more than the Earth's landmass per day, and we have about, as it says on the right, 2,000, I think, 400 or 500 layers of imagery for every point on the Earth's landmass on average. Wide variety of use cases for this data, some of them here, but I'll show you a couple of examples of disaster response. There's obviously tracking human activity around the world. There's defense and intelligence use cases of this, understanding threats, security threats around the planet, and providing and shedding light on those events. There's tracking floods and droughts, renewable energy. So we did a project recently with Microsoft, which mapped all of the solar facilities, utility solar facilities across the whole world, all of the wind energy facilities across the whole world. So just to give you a few examples, I'm going to touch a little bit more on some of the education and research ones, since we're here, but actually people in this audience know more about those than I do, so I'm also keen to learn. But disaster response, so this is before and after a flood, here, and obviously it can help us to respond to that. But much more importantly, we have data that helps us get ahead of floods. So we have a planetary variable, we call it, which measures the amount of moisture in the top 5 or 10 centimeters of soil pretty accurately at 100 meter spatial scale, so it's not super high spatial resolution, but it's every day, so it's higher temporal resolution. And with that data, we can tell if there's prospects for a flood, because we can look if it's saturated the soil, then it's likely that the next time it rains, it will flood. So you can give warning of flood at some level. Warnings of floods are much better than dealing with them afterwards, right? So helping with a disaster immediately after the event, during the event, and post-disaster analysis, and I'll get onto some of that in a second. But the most important thing is we get ahead of it and potentially evacuate people from those zones, or be prepared to, because we warn across the world where those floods might happen next. This is just another example, and here we actually show, this is the near-infrared band shown in red here, which pulls out crop type, and we can tell biomass and crop type and crop yield. And this is an analysis of how well all the fields were affected in this zone after that flood. And then this is another example of a flooding event here down in Brazil. It's not just flooding, of course, it's also fires, and earthquakes and tsunamis and so on. But I want to. So our data today is primarily imagery, and that's and sometimes we have these planetary variables that sit on top, like this soil moisture. We also have above ground biomass, the land surface temperature, all of these at a daily basis across the world. But where we're going is trying to unlock and enable answers to questions, sort of more like ChatGPT, but sort of like imagine a planet GPT, where you can ask text questions of the planet, just like you can ask text questions of the internet. And we've got this deep archive of imagery on which to train such models. And so we very much think that the AI systems enable to unlock that. And we started with what we call classical ML now, all the neural net, convolutional neural net models that helped us do things like identify ships, identify roads, identify buildings, identify planes. And so our users can select an area and say, I just want to know the number of ships in these 10 ports, or over time, or things like that. But where this is going with the latest generation of AI is really exciting, because it is enabling much faster modeling on top of the data. In particular, so I'll show you a couple of examples of this. And I think this slide was just to illustrate that we have this time machine. So one of the things that is interesting in doing AI analysis on top of our data is looking back through time. But so here's just an example of the, the question is, can you spot the ships and the planes in this image? And of course, it's a little bit easier for AI to do that. And we have 4 million images coming down from our satellites every day, which is rather too many to look at in person. So we, it was interesting when we first launched this fleet of satellites. The NGA, National Geospatial Intelligence Agency, which is the largest entity in the world of geospatial analysts, part of the US intelligence community. They showed my TED talk in their all hands. And apparently, this is what I heard later from the then director, who's now an advisor for Planet, and Robert Cardillo. He's a fascinating guy, and he said, the trouble is we need 4 million, I think he estimated that they needed 6 million analysts to analyze our imagery every day, which obviously broke their system, So obviously, the only way for them or anyone else to get value out of this is artificial intelligence. The great thing is that artificial intelligence enables us to democratize that so that you don't need 3,000 analysts or whatever they have to get value out of this data. Everyone can. Here's another example of a classical, as we call it, machine learning approach. We have worked with Microsoft also on this one, where it's a building by building damage detection. It actually tells you how much it estimates, is it 10% damage, is it 90% damage? And this took us many months to develop to work accurately in all the different parts of the world, because buildings look very different in different parts of the world. But now it works, and this is an example where we did building by building damage assessment across all of Ukraine to help understand what the costs will be for the UN. The UN asked us for this analysis to understand the cost of rebuilding Ukraine. But we've equally, afterwards, this took us many months to do this work, but subsequently, by the time it got to the fire in Lahaina, we were able to do it within 24 hours and actually help the people on the ground in the real time with that. So the American Red Cross was using it for their decisions making on where to bring medical supplies and so on to help people. So again, that's what we call classical ML. And this is, I guess, one more example of the value of our 8 spectral bands on our scan system. This was another analysis of Ukraine, of how every farmer's field was doing across the whole country. Which crop were they planting? Because we can tell crop type. How was the yield in each of those fields? And and it's also overlaid where it was under Russian control versus Ukrainian control to help with food security issues. A lot of countries, of course, Ukraine relied on its food production, but a lot of other countries relied on Ukraine's food production. It was about half the grain supply for the World Food Program, which all the poorest countries of the world get their grain from. So a lot of it was coming from here, and it was critical to know where was it and who was affecting it. And some investigative journalists also used this data to then find where the Russians had been illegally stealing grain and taking it to Turkey and Syria against international conventions, and that led the West to be able to impose sanctions for that specific thing. So that gives you a flavor of... But I wanted to give this example of large language models on top of our data. This is a first attempt we did with synthetic, which was about this time last year, and a lot has gone on since then. But this was where NORAD actually asked us, could we find where the Chinese spy balloon was over the United States? And we were like, wait, do you not know where it is? Presumably they knew where it was, but it did evoke the question. Anyway, so we knew this was like the day after or the day before they shot it down, and then we knew roughly where it was at that point. Then the next question was, where had it come from? And so this AI model had never seen a balloon. We sketched a balloon using a hand sketch, what it might look like, but we knew it would have this parallax effect. It's not actually moving. This little video gives it a little bit of suggests that it's moving. It's not. The satellite's going over the top and it's at altitude, and so we get this parallax effect for any moving objects or objects at altitude where you see the different color bands at different positions. So we knew it would be spaced out like that because of these altitude effects, and it makes it particularly simple to find. But this model had never, this AI system had never seen a balloon, and within minutes we were not only able to find the balloon, but trace back through what was equivalent to, it took 2 Earth landmass equivalent areas, because we had to trace back through time in our time stack of imagery to try and trace back where it came from, using a bit about wind patterns, and then eventually found where it launched from in China. And then the next question, of course, is where else are these balloon programs going on? What's the day-to-day events? Where are they flying, and why? And this is not just that. I mean, we can detect planes and aircraft across all of China, or all of the solar farms across all of China. And this now is something that can be done in minutes with one or two people. This used to be the job of huge spy agencies or so on. And I think the power that is being unlocked with AI is just tremendous. So it is democratizing so that what was once the job of thousands of people can now be done by everyone. And I think, again, that's the sort of the magic here. Imagine if you just want to search for where's the deforestation in the world, what's that similar pattern, where would you predict it to be going next based on the present patterns, and so on. So that's a little bit about AI. I really want to touch on a few other use cases that people have used our imagery for, especially in the sustainability realm, given the topic today. So this is a map of the coral reef system around an island, and this team that was led and funded by Paul Allen just before he passed away, sadly, looked at all the coral reefs across the entire world's tropical zones and identified the different kinds of coral systems. I was surprised that we could do that, but down to 10 or 15 meter level is where most of the corals are at, and it turns out to be visible in our data. And they provide these alert systems. And I go scuba diving a fair bit, and I used it on my last trip because a lot of the systems are under attack, and you see bleaching events, and it's sort of sad to see that, but also it helps you to understand where we need those efforts. So they warn coast guards of bleaching events so that they can get ahead of, or illegal shipping, I should say. And then the bleaching events, there's relatively little we can do, as I understand. There's another project that we have with Norway and the United Nations to track deforestation in 64 countries. And we do that and provide these daily alerts of deforestation events across basically the tropical belt of the world. This effort, together with some work with the Brazilian government last year, together it was a wide variety of actors, but it led to a 55% reduction in deforestation rate in Brazil, in the Brazilian Amazon over the last year and a bit. They confiscated $2 billion worth of equipment at the same time, because basically we do an AI on top of this that gives them a weekly alert of any new deforestation events, and anyone can they can then use that. And that's normally, they actually find it by we look for new road starts, and if there's a new road, it's normally a sign of illegal something, whether that's illegal deforestation or narcotics or illegal mining. but they then fly in helicopters or whatever, and they stop that activity, arrest people. They had 3,000 interventions based on this system last year, and as I said, the resulting reductions in deforestation. You need a government that actually cares about it, but the data helps when you do. But this is not where we're stopping on forests. This next slide is about a forest carbon map. So basically measuring the amount of carbon in every forest around the world. And it actually can do it, so we're going to be publishing, starting this year, a 3-meter map of the world's forest carbon, and this does this by looking at the tree species type, at the canopy structure, the canopy width, and then a load of ground truth using LiDAR in certain specific forested regions to then calibrate to provide an estimate of the amount of, so it then uses a model that's been calibrated to estimate the amount of carbon. So every quarter we'll be publishing a map of all the carbon in down to pretty much the individual tree level across the Earth. There's a lot of carbon efforts to do carbon financing and carbon markets. And of course, to underpin them, you need accurate and scalable carbon measurement systems. I think most of the challenges of carbon markets have been either they have been accurate but very unscalable, like people measuring tape measures around tree trunks in individual little projects, or they have been global but not very accurate, which has led to a lot of greenwashing. And the hope is that this system can underpin efforts in carbon markets. And just touch a little bit on university uses of our data. We have universities around the world. We have about 30,000 research users of our data. So if you're not one of them, join the club and join in. It is free for you guys, at least up to a certain volumetric limit. I don't know exactly what it is, but kindly, NASA helps support. Any federally funded researcher can access the data, and we have a special partnership with Stanford to help everything else, and there may be certain volumetric restrictions, so if you start searching and downloading the entire database, you might come up with some limits, but generally the goal is to enable people around the world to access this data for research purposes to help us to understand the planet in line with the mission, otherwise we get fired. So this is the papers that the last few years, you can see it's definitely been going up, and the different aspects of Earth system sciences on which people are doing it. I'm really pleased to see how diverse it is, ranging from cryospheric research to hydrosphere and so on. 2.7 papers per day. And having done a few papers when I was a PhD student, I know that that's hard work, so it's a lot of effort. Here's a few examples I just wanted to give. This is from the University of Copenhagen, who do a lot of frontier work on forest modeling, and generated these custom mosaics, and then revealed the count of trees was wrong and course corrected. It's kind of cool. And then this was a permit enforcement case, actually, from folks here at the Reg Lab, which was, I love seeing these applications out of earth sciences, and there's been a number here at Stanford. There's some on poverty research that I read in Nature not too long ago, leveraging our data. And this one was on food security. Some folks at Clark University looked at, all the smallholder farms, and basically giving insights for food security across the African region. But that's just the beginning of where we hope to go. We very much believe this is the tip of the iceberg of the potential, to my starting comment. We need all hands on deck to help us to save the planet, and this data set is just meant to be one tool that really helps with that. So with that, I'll finish here and open it up for questions. Thanks very much.
Well, thank you, Will. That was amazing, just outstanding work and what you've achieved in 14 years. Because I don't think 20 years ago, for example, one could have imagined, and the compute power was not quite there for AI to do all of this. So this is like an amazing time to be a graduate student or even an undergraduate student. So let's open it up for questions. What we're going to do is that we have some questions that have come from the audience. These are pre-submitted questions. We're going to go back and forth. So let's start with an audience question, then we'll come back to the pre-submitted one. Does anyone have any question? Or while you're thinking about it, let's start with one out here.
Do that.
Yeah. So here's the first question. So much of planet's work is inherently geopolitical. We saw a little bit of that. How do you think about the ethical boundaries when engaging with foreign governments?
Yeah, I think it's a great question. Firstly, let me step back and say that security and sustainability are not different domains anymore. And people have really understood this more and more. The Syria example, I think, was perhaps most specific on coupling these two when a drought, climate-induced drought, led to food insecurity, led to civil strife, civil war, refugees around other parts of the world. It's a security situation. And the world is going to face more and more of those. And we tackle this head on. We work with security agencies, ministries of defense around the world, and we work with NGOs and academics that are doing sustainability research, and we encourage them to work together. Because, as I said, we're going to see more and more security events driven by climate. We're going to see, hundreds of millions, if not billions, of refugees. What we're seeing on the southern border of the United States right now is just the tip of the iceberg of what's coming. And we're going to have to get used to that, and that's going to be increasingly climate-driven. And so I think that these things is coupled. I think there's... but to the question, we do realize that this has a lot of political value, geopolitical value, and we're very careful with that. Our default posture is open. Let as many people have access to the data, and they can triangulate the truth, and that generally that will help and foster peace and security. In fact, if you look back at the Cold War or history in general, you'll find that times of tension were typically when countries didn't know what each other were doing. So I generally find that and think as a thesis that intelligence of one country or another is generally a good thing. But even more so if they share it, the same piece of data. So they're on the same page about who's got what where. And so it's when there's uncertainty that trouble tends to take off. I mean, we saw this in the Cold War with the Cuban Missile Crisis, or this equivalent crisis when the US put missiles in Turkey and the Russians didn't know, and that was when the war almost got hot. We are very careful who we work with. We default to open, but we have an embargo list that we don't work with the UN, the US, and the EU's list of embargo entities, but we also have an ethics committee, which looks at every new potential customer and evaluates them against our principles and our values and ensures that we think that they're going to do something that's positive for the world, for example, not targeting civilians or something like that.
So I'm so glad you put those guardrails in place. But so no president or prime minister has tapped on your shoulder and said, can you just blur that image a little bit?
There have been, people casually make those sort of requests, but not anything formal. And I think, that's a super important principle, that we don't manipulate data and keep it really the original.
Terrific. Okay, so from the audience, any questions over there?
Thank you. So the spatial resolution you show is pretty amazing, but some of our research require high temporal resolution. And my observation is like your polar optic satellite only give you probably twice 2 images per day over a location. So I'm wondering,
what do you want?
Like a 24-hour full spectrum throughout the whole day.
You mean you want live?
No. My question is like, now you have AI, this tool, probably you can get some other help from some geostationary products and probably do some extrapolation and recover the rest of the day.
I think, I think that's a great strategy to, as you say, recover different temporal or spatial resolution by looking at the different, you have weather sats that are like 20-minute revisit rate, but at multiple kilometer resolution, to MODIS that's at daily at 500, ours at 3 meter, and then you have much higher resolution systems. I think, as you say, AI can really help us to bridge those gaps. But also, if you have obviously the physics drives our resolution and cadence, the number of satellites, the size of the telescope, the orbit. It's pretty simple physics, it becomes more and more expensive to build bigger telescopes in space because the launch costs still are a lot, even though they're coming down. So our goal is often thinking about the cost per the cost per pixel of unique and interesting information to drive our considerations, but also what customers, of course, say. But the fruit in the gaps there is a good point.
So the next question out here is, okay, so what are the main challenges in converting raw data into useful, actionable insights on the ground for conservation and restoration? This is right in your bailiwick on conservation and restoration.
What are the main drivers? What makes it harder? Challenges? Well, I mean, I think, conservation projects are really hard, and they take groundwork. You can't get around it by satellites, obviously. But what you hope to do is make it more efficient and more effective. Like if you're trying to do sustainable or regenerative agriculture, where in the field is there having a problem and why, and how do you limit intervention to that area and so on? Or in rewilding projects, where's best to start? Where's taking off in your experimental approach? I have a project myself that involves a property that has about 1,000 hectares where we're trying to do rewilding. And my main goal there is to understand how hard it is on the ground so I can help inform our customers. But obviously, we try to work with, I think the challenge today is that the data is still, as this question is getting at, hard to access. And you tend to need people with PhDs in GIS to get some value out of it. But I think it is rapidly getting easier, both because of conventional tools and AI. We're doing a lot of work with a platform we call Sentinel Hub, which enables basic tooling on top of our data to enable people to build some of at least the simple tools that enable you to get going. Today, most of the conservation work's done by large NGOs that we work with, like the Nature Conservancy or Conservation International and so on, where they have geospatial teams, or World Resources Institute that is more specialized in technology that helps conservation. But in time, I really hope that the smaller NGOs will be able to get access. I think we've seen a huge take-up in university settings like this, but less so in NGOs, and I think it's because of that. Researchers, of course, are used to having to deal with tricky data sets because they often invent them and then figure out how to get value from them, right? But NGOs aren't used to that at all, and so very few of them have strong technical teams. Please go and help them.
Hi, Will. I owe a big part of my professional development actually Planet. So really great to see this conversation here. My question is actually related to something you mentioned earlier and the other audience question about, we have already seen AI used in GIS for a long time. Most of the time has been using to extract further additional insights. So data fusion, change detections. Now we're seeing more generative AI that's able to generate more data, kind of like hinting to your point. How do we draw the line and how do we ensure the data authenticity, the truthfulness? How do we know when the data is actually captured from space versus not? And what is the implications there?
That's a great question. We're talking a lot of that right now at Planet about super resolution techniques, and of course some get sort of to a place where they're inventing stuff and others don't. And where do you draw the line that's physics based versus that? And yeah, I think that's, obviously you would hope that at least we label these things clearly, right? All actors, and I think that's certainly a principle that comes to my mind of how we've got to act. Like, is this, synthetic data or not? And labeling that very clearly. Similarly with propagation into the future, you can, somebody was showing me recently, they were doing a bunch of work in civil government and looking at civil infrastructure and its effects, how it's affected by climate change. And where they didn't have maps of sewage systems, because because that municipality didn't have it easily available, certainly not digitally, and there's a lot of they extrapolated the sewage system based on the prior data, and I was like, well, that's interesting. It's obviously not going to be exactly where it is, but it probably has a good guess in many cases. But you've just got to clearly have a different label for that.
Yes. So the other question, and I'm going to adapt it a little bit, is what are your thoughts on cost-effective accessibility of high-resolution imagery? Actually, let me adapt this a little bit. It's not only the cost-effectiveness, but the ease of use, as you were talking about. And I was wondering, when would it be possible, let's say we wanted to have a hackathon on satellite imagery amongst the undergraduates out here who have taken CS 106A, which is like the opening, like 90% of the undergraduates take that. And if they have to use satellite imagery to query something, right? Where are those ships going around the world of this XYZ size? How far is that?
I don't think that's far at all. I think the basic tooling exists for that today. I mean, you name the date and we'll have the hackathon. Let's do it.
Hi, thank you so much for a really nice presentation. And I also have a question about the satellite images in time dimension, because echo to the other question from the audience. Because when we talk about sustainability, we also care about like the scale of the time dimension. Like a lot of questions are a couple of decades or even like millions of years. And the problem is that when we look back to the history, we don't have like much history. And I'm wondering like if you want to share any insights about this type of challenge, and also like if your team like has like worked on this type of problems.
Say more about the challenge that you're finding.
Yeah, a lot of the time we want to look back to the history for a couple of decades or even like 100 years. But for that goal, like we probably don't have enough images of the satellite because we may not even like launch it. So in terms of those challenges, like have you ever done any like similar work to solve that?
Well, I've tend to find it's hard to go back in time and get better data. So unless somebody's here in the physics department inventing time machines, you know, I mean, I don't want to say, I mean, obviously we're trying to create this record of the planet on at least a daily basis. To the earlier question, we'd love to have it more regular, higher resolution, more spectral bands, all the kinds of improvements, radiometric quality and so on, that would enable it to have more value. I think you can do a fair bit with interpolation between data sets. We have seen some great work on data fusion, where it involves both fusing different data sets, in particular Landsat and Sentinel, which have super high quality radiometric accuracy on their spectral bands, combined with a higher temporal frequency and spatial frequency of our imagery, and which extrapolate in between to, for example, if there's clouds, it will have a guess. Now, to the earlier point, we then have to label that, well, that's a guess, right? But if you have before and after, you can often guess quite well for things like expected crop yield at this point, right? And that turns out to be useful for agriculture. Obviously, you have to drive those cases a little bit specific to the use case that you have in mind. But I don't have any generic answer to your question. I think it's I can't wait to see your paper that solves it.
So I'm going to combine a few questions out here. Let me ask you about Planet. I mean, you obviously are specializing in taking this amazing satellite imagery, et cetera. In terms of applications, that requires some domain knowledge, right? And are you planning to develop those like different, you know, themes or thrusts within Planet? Or is there where a partnership with the university can help or can be of value to you?
Yeah, I mean, definitely it's a partnership approach. We don't claim to be experts in all the domains that we serve. We do have some experts in agriculture, in disaster response, in so on. But we can't. You know, the number of applications exceeds the number of people that work at Planet. You know, yeah, I mean, I think it starts with the universities. So back to your point. So universities are where we typically find the best research on, say, how you can leverage satellite data and AI or analytics of some kind to enhance productivity or sustainable practices in agriculture. And we've seen a lot of that. And then what's super important about that is not just that the commercial companies then pick that up and then can help scale it, but also the governments can pick that up and then help enforce whether it's subsidy programs or sustainability programs that they have for agriculture. And I think the same is true across the board. And I just say to this audience, like, don't forget how much governments look to university research to base their decisions. And we're in a situation right now in the world where no one's doing sustainability stuff because nobody believes it's measurable. And so what's the point of doing sustainability stuff if no one's got on the same page, right? And we obviously have to get out of that loop. And that's part of what Planet is there for. But it can't be the only actor. We have a self-serving interest, despite my statements about the public benefit corporation. We're still a corporation. You know, we have our own financial interests as well. It's super important that universities say this is a valid way of checking whether you're using tilling practices of this kind or not according to this subsidy program, and therefore encourage, so that we can't hide behind the idea, oh, sorry, we can't do sustainable agriculture, we've got to wait because no one can check. Well, yes, they can. And that's how we move forward. And, you know, my hope is that we move to, I mean, some of these things I think can enable us to transition to a sustainable economic system much faster than the policymakers think, because the policymakers don't know about new technologies. So it's our job to spread the word about that.
Yeah, thanks for a fantastic, really inspiring talk. And I just wanted to follow up on what you're discussing right now. Obviously, at one level, really trying to open up people's thinking, especially among leaders, decision makers in a lot of contexts, to see what's possible and aspire to something a lot better. But at the same time, I just wonder what, given that you've been at this for quite a while, that your passion, as I remember you mentioned at the last time you were at Stanford, really is on nature and biodiversity. And that just was not on the table when you got started. And I wondered how you've seen things change. What kinds of what demand do you see among the people clawing at your sleeve to do this or that, you know, around the world? How's that changing over time? And if you have a moment, what really lunatic things have come at you as well?
Yeah, this is a little different from Gretchen's, but I'll ask it now. I'm curious about your plans for the oceans in the future. I understand in the startup phase why you would focus on coverage of the terrestrial environment, but 71% of the planet's the ocean, and with Tanager and the conversion from multispectral to hyperspectral, you know, I can't help but think it's going to be a key ingredient to monitoring CDR, carbon dioxide removal in the ocean, particularly those that involve altering biological systems or producing precipitates in the ocean. So that's it. But
Oceans, and then how did...
Yes.
How does, yeah.
Well, I mean, so my passion is very much nature and but what I've seen that's taking off the best in terms of, I mean, the world is still placating sustainability. It's sort of saying, hey, yeah, maybe we'll think about it sometime. I mean, when I was at Davos this year, that's what I felt. It was, you were there too, so you know, you tell me if your impressions. But like the world leaders are sort of like, yeah, but sustainability, that's cool, and then they don't do anything. You know, we have to hold that accountability, and accountability comes from these sorts of systems. And public accountability comes when those systems are public. I think forest carbon is the closest place that we are ready to scale, where we could say globally, every company on the earth, every country on the earth has to balance their carbon books. There's no excuses. Just like you have to balance your finances, you have to balance your carbon books. We're not there on nature yet. We haven't even agreed what we're measuring, yet let alone how to measure it, let alone integrating that and accepting that into our economic system. We're a long way off. Luckily, they're very correlated, as you are aware. So I think, you know, the best idea I hear is like, let's bootstrap nature onto carbon for the minute, because that's most close to, despite recent setbacks with some of the systems, most close to being able to get from the billion-dollar scale that it is at present, not to measure it only in dollars, because that's not what we really care about, but it is a sense of how where we're going, to the trillion-dollar sort of scale that we need it to be relevant to changing our economic incentives around the planet, to actually preserve nature and therefore not breach straight through the planetary boundaries that we all care and love. No's crazy idea has definitely been putting something to do with cryptocurrency ledgers and shit in space, and I'm like, come back to me when you've got a plan that actually helps the planet. I don't understand much of how crypto world helps the planet in the first instance. Putting it in space didn't seem to help that. But they were offering us quite a lot of money, but crypto in space, but I still didn't understand the purpose, so I said no. Yeah, so the oceans, we'd love to do more in the oceans. And the point's not lost, obviously, about the amount of nature and value that we have in the oceans, and you mentioned the climate piece of it, obviously, relevant too. We try to do that where we can. It's just a capacity limit of getting all the data back. But actually, AI can really help with that, as we, and it's not all about AI. So I've mentioned that term too many times, as so many other lectures must do. But if you can only send back the pieces that are most relevant data or the synthesized data, it's a data bottleneck. It's getting the data back from the satellites down to the ground. So it's not about imaging. We could image more of the oceans. We can't get the data back. So we want to put, if we could put simple algorithms upstairs that filter the data to the things that we need, and then just send down that summary data, that would actually make the problem sufficient. And so our next generation of satellites are all having a lot more compute on board. I mean, actually I called our last generation of satellites the first machine learning first satellites, both because of the volume of data, but also because the 8 spectral bands that people can't look at, or the combinations. We were hoping that machine learning would pull that out and get value out of that in ways that the human eye can't. And the next generation will be even more along those lines, because we have so much compute on board that we can deploy a lot of that so that we can continue to do more of the ocean. So that's one way out of that conundrum. Meanwhile, we'll just focus on the most biodiverse regions, because that's really critical. Obviously, there's other regions that matter for other things, whether it's weather or carbon cycles, as you were saying. But we'll get there, and if you have specific requests, let us know.
This is really, you're talking about AI on the edge. This is literally the edge out here. Okay, right. Okay, so there's one question over there, and then Cam Moeller after that.
Hey there, thanks for answering my question. I was wondering, with your carbon mapper project, where do you see it going? And moving beyond methane and going to CO2, what kind of things can we see in the future from Planet in terms of like actionable timescales, like live detection of methane leaks from wells, or like these kinds of like applications that can be actionable and prevent emissions, and also for monitoring for like UNFCCC like guidelines.
Yeah. Well, look, I mean, actionability is why we're doing this. The Carbon Mapper is a non-profit that's set up just with that purpose. And it was a consortium with NASA JPL building the instrument, Planet building the satellites, and this NGO, but also the California Air Resources Board, because the goal is to help them with some of the most forward-leaning folks on looking at methane at all and trying to track it. The goal is to help enforcers of regulation on both sides of it, but the countries and regional governments, to give them actual information about violators of whatever regulation they have on methane, and then on the company side is to get ahead of it, right? So it's and that's the approach. There's a part of this project that's a digital public good, which will be a monthly base map of major methane emitters around the world. And part of it is a commercial business where we will sell their data to companies to try and not get fined. And we hope that going both sides of that will be the fastest pinch on that and that problem. But of course, action is where it's all at. Yeah, and that's what we're trying to get to. Furthest back? Yeah.
Yeah, I wanted to echo, first of all, what Gretchen said about how inspiring your work is. And then maybe just follow up a little bit on the question about trust, because I think public trust in science and public trust in your data in particular is such an important part of the data that you provide. I mean, I hear what you're saying about how you avoid AI hallucinations, or at least warn people about them. But I think maybe part of what underlies the question is, you joked about governments asking you to blur your data. Maybe it wasn't a joke, but I could imagine so many other opportunities that people could create for themselves by speaking to some of your data engineers and having your data be a little different than what it actually is. And so I guess I was wondering, what conversations are you having within your group about lineage, traceability, reproducibility? How can people be sure that data that is said to be your data really is from you, and that you're really being good stewards of the actual images?
Great question. Yes. And obviously not just particular to planet, but how we deal with data generation and content generation writ large as a society. We're doing some specific things to do with hashtagging type technology on the satellite when it produces the image, so that we can always tell if someone's manipulated any one pixel of that image and always have that heritage. I think we have to have common standards of those around in our society. It also makes me bring up a slightly broader thing. I mean, we're obviously as a society facing various different challenges, climate, biodiversity loss, so ecological ones, if you like, and then there's information ecology, and then there's sort of the security as the balkanization of the world, and all those things are interrelated. You know, information matters for what's going on in Ukraine as it does and what's going on in Brazilian Amazon, and we need a shared notion of what's true, and we're losing some of that. I think social media isn't helping this. We're seeing that become harder. We can't agree on whether the climate is changing, or who caused it, or whether COVID is real, or anything in between. My hope is that, and aim more than hope, is that Planet can help with all three of those aspects: the ecology, the information ecology, and the, if you like, political economic ecology, in bringing transparency that helps us to understand the truth of what's going on. So to your point about integrity of data, it's absolutely critical to that. It's the foundation of that. So the import of it, as you're emphasizing, is not lost on us as a company and the role we play. Obviously, as I said, it's an ecosystem approach, because we've got to get this all right. We've also got to get the social media companies to care about information ecology, which I think, frankly, we're not doing very well at right now. And understand the in-between factors in between information ecology, sustainability and ecology, and the geopolitical ecology. I hope global transparency helps. The theory of change is transparency helps accountability, helps us to address all these problems, and that it helps all three of these. That's our goal.
Before we end, I'm going to ask you, I know I'm getting the science to end, but I have to ask you a personal question. You're obviously a busy guy. You have been, this is an amazing company. There's, I'm sure, a lot of customers looking. What is one thing that you wish you had time to do, you just don't have any bandwidth left, that a student could work with you?
Well, there's no real small project I have in mind. I just have a big project. It may take more than one student. But, I mean, it's sort of a conversation I was having with a few people before we got started with this. We need a sort of global, when I was at NASA, we would have mission control systems for every spacecraft that we sent up. And we would have people around the clock measuring those systems and making decisions about that spacecraft, whether it's anything from the International Space Station to a small spacecraft. Obviously, we're all on the spaceship Earth, as Buckminster Fuller helped to evangelize, and we have to have control systems. So where's the Mission Control Center for Spaceship Earth? And the challenge today, I think, one of it is that no one agrees on where we're at. I meet environment ministers all the time that couldn't tell me how well they're doing or not doing on emissions to deforestation or anything else. So where's the sort of mission control center for Spaceship Earth that helps us to track it's not so much a mission control, it's more like a, let's say, a dashboard of how we are doing, an Earth dashboard, but it has to be unified. There's so many efforts, but that so many efforts means that that's why no one knows where to look. So how do we get to a more, it's not so much the, do we have the data sets, it's how do we collate them into one that any one country's environment minister or citizen who wants to help the problems can go, okay, well the big problems is I live here in Santiago and here's my nearby parks and here's where I could help locally, or this is where we're worse than our next door neighbors in Argentina and I would like to do better. So, it becomes a race to improve according to standardized metrics as opposed to everyone saying, well, my scientists say this, So they hide behind that all the time in the COP. Right? So what would an Earth dashboard look like that everyone agreed is the main place to go look at? So again, that's not one student project, but that's the thing that I think is most missing, and classical problem of coordination, Google has a great one on measuring water quality around the world, but it's just one of the 177 things that we need to measure on this global dashboard. So how do we put it all together into a synthesized system, a bit like our world in data has for some sorts of data sets? That would be my vision.
Well, with that call to action, let's give Will a big round of applause. Thank you so much. Thank you so much.